soon. Yeah, we are now recording. Let's go from current slide here. And while the projection is coming up, let me go through a few announcements, okay? You get to be a bit more tedious as the term winds to an end, but hang with me. Student course evaluations. Everybody either done them or planning to do them, right? Excellent. Good. Okay? That's done. Now, let's talk just a little bit about how the term's going to play out. Okay? Now, today, Wednesday, next to the last class, okay, we have class today and Monday, and then the final exam is, I'll give you, actually today before you leave, get your final exam, and you can work on it over the weekend, and then any additional stuff we cover on Monday that you need for the final, you can still work on that. Okay, so that's done. Let me briefly go over office hours. They almost are going back to what they normally were, okay, originally. Today and Monday, of course, I was in the office 8 to 8:30, or approximately that. I was down in the copy room more time than I was in the office, but anyway, technically those are office hours. And later today from 5:30 to 6, I'll be in the office mostly, okay? I've got to close up the class up here that ends at 5:25, and sometimes that takes me more than 5 minutes, but yeah, after that I'll be in the office pretty much, okay? Only half an hour, so it's not much. Tuesdays and Thursdays have been really weird for the last several weeks. Finally, I think they go back near normal, okay? So tomorrow and Tuesday, I'll be in the office from 8 to 8:30 approximately, and then I'll have class from 8:30 to 10:45. So from 10:45, now for the last several Tuesdays and Thursdays, I've had to go to the Birmingham campus sometime in the afternoon. I don't think I have to anymore. I got all the evaluations signed and turned in. I've got our hearing has been done, completed. No more meetings because of that. So tomorrow and Tuesday, I should be in the office from, in addition to 8 to 8:30, 10:45 until 4:15. I think originally I said 4:30, giving myself half an hour to get to the Birmingham East Campus for a class. I found out I can't quite make it in that time and get the class set up and everything else. So now I'm leaving at 4:15 rather than 4:30, or at least that's what I'm shooting for. So tomorrow and next Tuesday, 10:45 until 4:15. Then I'll be on the Birmingham campus until 6:30, more like 7 o'clock, but the class ends at 6:30. Okay. All right. Now, final exam, like I said, I'll be giving you that test today for you to start working on over the weekend if you choose. That's up to you. But when is it due? Well, anytime Monday, Tuesday, Wednesday, or Thursday. I've just given you my office hours for Thursday, or today, Thursday, Monday, and Tuesday. Let me give you my office hours for Wednesday and Thursday, final exam week. Okay, that's all we got for a final exam week. On Wednesday, I'll be in the office from 8 in the morning. We will not have class here, but if you want to come turn in your test, you can. But I'll either be in the office or up here in the classroom, one or the other, from 8 in the morning until, unfortunately, 12:30. Okay? Why? Because they called a meeting during final exams at 1 o'clock. Okay? So I have to go to the Birmingham West Campus to be there from, I think the meeting usually goes about 2 hours. Hopefully no more than that. Hopefully less than that. But let's say 1 to 3. And then after 3, I'll be on the Birmingham. I won't be driving back here and wasting another half hour. I will just stay on the Birmingham West Campus in B122, and I'll be there until at least 6 o'clock. Okay? So if you want to turn in your final on Wednesday, get it to me before 12:30. If you want to get it to this campus after 12:30, slide it under my door, room 265. If you're going to be on the Birmingham West Campus, bring it there after 3 o'clock, or even before 3 o'clock. If you take the 122 If Miss Saxton's there, the secretary, then you can leave it with her and she'll give it to me when I get out of the meeting. Okay. And let's see. Then Thursday, I'll be on this campus from 8 in the morning until 4:25, maybe closer to 4 o'clock. I probably will leave a little early to get over there. So 4 to 4:15, something like that. And then I'll be heading to the Birmingham East Campus. I will not be coming back to the Bessemer campus after 4:15. So please get me your final before 4:15. Or you can take it to the Birmingham East Campus. I'll be there from 5 until 6:30, probably closer to 7 o'clock. So that will be, you can bring it there. Now that's Birmingham East Campus, the nursing building. It's the Ethel Hall building. Room I think they call it D114. Whatever, it's on the, 214, on the second floor of the Ethel Hall nursing building. All right, let me back up. I missed something in there. Well, two things. First, Monday, I will be returning every paper to you, except the research papers. I can't return those because periodically they ask for samples of student writing. So I have to hang on to those. But all of your tests, I've returned test 1 to just about everybody who's been here. Test 2, I'm still waiting, I think, for one person to turn that in. Let me make sure on that. Test 2, got 1. Let's see, no, okay, she withdrew. Yeah, one person to turn in test 2. Test 3, most of you, I think all of you have turned it in, but I've still got 1, 2, 3, 4, 5 who have not turned in test 3. Those will be coming back to you Monday. If I don't have it, that's a big 0. Okay, so please get, I'm talking to preaching to the choir here, but the others, hopefully they're listening. So I will be returning all those to you on Monday. Okay. Now, here's one other thing. Technically, your final is due on Wednesday. If you want to wait, if I'm not here, like I'm in that meeting, slide it under my door, or bring it Thursday. I'm happy with Thursday, as long as it's before 4 o'clock, okay? Because at 4, or shortly after 4, I've got to go to the Birmingham East Campus. Now, the reason for that is I'm planning, I haven't gotten approval for this yet, but I'm planning not to be on campus the following Monday. That means I'm getting all my grades in Thursday afternoon, okay? So if I haven't received your final by 4 o'clock on Thursday, oh, he came in. I was going to try to sneak this by Terry, but he came in. Okay. Yeah. Morning. If I don't have your final by the time I leave this campus at 4 o'clock on Thursday evening, I have to give you an incomplete. And then when I get back for fall term, if it's under my door or wherever, I'll grade it and change the I to whatever your grade is. So please get me your thing. Now, I haven't gotten approval to be off Monday yet, but I hope that they'll grant that because I've need to be out of town over the weekend. And just rather not have to drive back and drive back again. All right. Any questions on how we're going to wrap things up? And please do the student course evaluations. No questions? All right. Says here, evaluate this definite integral. Okay? This is Chapter 4, Integration, 4.5, Integration by Substitution. The last section, the last example in the chapter, page 304, example 10. How would you proceed? You tell me. Anybody? How would you proceed with a problem like that? Where would you start? I can think of at least a couple of ways to proceed. You tell me how you would proceed. Say again? Okay, so let's see. Let me get my pen set up. All right. Now I heard the U in there. Is there a let U somewhere in there? Let U equal what? Anybody? Is that what I was hearing? Maybe I misunderstood. Okay. What do you want U to be? Oh. I decided to show it. Good deal. Good to see. What's that? Nice shirt. Okay. Nice shirt. Thank you. I'll tell my wife. Okay. I don't buy shirts. She does. Okay. Nice shirt, by the way. All right. All right. Anyone decide what U is going to be?
I'll say sine.
I think that's a great idea for it to be sine x. And then what's the next statement? Then du is equal to, what's the root of a sine? Cosine x with one other little thing. It's in dx. Perfect. Okay. Now, all right, where do you proceed from here? Frankly, in my mind, okay, we're in Chapter 4, Integration, 4.5, Integration by Substitution, the last section in Chapter 4, and we're on page 304, Example 10, the last example in the last section of Chapter 4. Okay, we've gotten started here. We're choosing a U, figuring out what the du is. Now, where would you go from there? Again, I can think of at least two paths to take. There may be more than two, but what would you do? Anyone have an idea? Help me out here. I'll give you a hint for one path you could take. What's the F word? Hey, what? Yes? Oh, you may not have heard this, have you? Someone who's been in my class before, tell them what the F word is. Factor, of course. What else could it be? Don't answer that question. Okay. So let's factor that, and that'll be the integral from minus pi halves. Now, you don't have to do it this way. It just, to me, this makes sort of sense, over pi halves. Now, what can you factor in that integrand? Okay. But since we're going to let u be sine x, let's leave sine x alone and just factor out, say again, cosine x. Okay. So that would be sine x, sine cubed x, plus sine x times cosine x dx. Now, you don't have to do it that way, but do you see why I chose to do it that way? So here's your u, that would be separated out here. And here's your du, and that's separated out there. So doesn't that work like a charm? Say again? Yeah, you can write the du, and you can change the other part. And what would that be? Integral of, write it in terms of u. Say again? Rewriting sine cubed u as in terms of u. What would that be? U cubed, okay. Plus u, me? No, okay. Times, and what's cosine u? It's a cosine x dx? Du, okay. Now, notice I left off something. What did I leave off? Ooh, no, we took care of the cosine. Because cosine x dx is du. We took care of that. Okay, but we factored out, right? That's why I had you factor. Okay? Now this is the only way you could do it. To me, this makes sense. Okay? But what have I not done? Yeah, do with the limits. We made the substitution with the variables. We haven't made the substitution with the limits. So let's go over here using this fact. This is the limits on x. When x is equal to minus pi halves, what's u? Sine of minus pi halves. Okay, that's what negative pi halves is. And what's the sign of that? Nah, very good. So your u is going from minus 1 to, when x is equal to pi halves, what's u? 1. All right. Now we've got our limits in place. Right? Okay. When we change from x's to u's, we also have to change our limits, because the x's go from x equal minus pi halves to x equal positive pi halves. So here's where we made the decision to go from x's to u's. So plug them in. When x is equal to minus pi halves, u is equal to minus 1. When x is equal to positive pi halves, u is equal to plus 1. So now we've got our integral all set up in terms of u's, not x's. And this is hopefully not a bad integration to do. What's the antiderivative of u cubed? Anybody? Antiderivative of u cubed. U to the u's fourth, go up 1, antiderivative, over 4, next, plus u squared over 2. Oh, you may have been doing the u squared over 2 first. I'm sorry. Didn't mean to buzz you too soon. And then we do this, evaluate this from minus 1 to 1, right? All right. So let's plug in the plus 1. 1 to the fourth power is 1 over 4 plus, and 1 squared is over 2 minus negative 1 to the fourth is negative 1 to the fourth is 1, so that would be another 1/4, and then minus a negative 1 squared is 1 over 2. And what does that add to? Tough math today. 0. Oh, but we knew that, didn't we? This is certainly in the u's, an odd function of u over a symmetric interval, which means whatever you do on the left-hand side is exactly opposite what's on the right-hand side, and those two add to 0. The areas on the curve add to 0. Which, if we had just paid attention to our theorem, integration of even and odd functions, we would have seen that was the case. Okay? Now, that was one way to do the problem. The way they did it in the book was deal with the oddness of it. Okay? But I'll let you tell me which way you wanted to go, and you did it, so that's perfectly fine. Okay? Any questions on that? Oh, let's see how they did it, since we're there. Can I erase? Okay? Okay? Let f of x, this is another way to do the problem. Let f of x be sine cubed x plus times cosine x plus sine x cosine x. And when you plug in a minus x for x, you notice you get sine cubed of negative x times cosine of negative x times sine of negative x times cosine of negative x. Now, why would you even think of doing that? I wouldn't. Okay, but they did, and it's perfectly legitimate to do that. Well, Sine itself is an odd function. The cubic function is an odd function. So the odd function of a negative value will be minus sine cubed x. Okay? The principle of odd functions. This, though, is an even function. So an odd times an even is odd. Think of it as pluses and minuses here. Okay? And this would be, as we just said, sine of negative x would be minus sine of x. Cosine of negative x would be cosine of x. And negative times positive is negative. So both of those become negative, as they show here. Negative sine cubed x, cosine x, negative sine x, cosine x. And this is exactly the opposite of what your f of x is. That's minus f of x. So we've just established our integrand is an odd function, perfectly odd function. What are the three possibilities if you do this kind of analysis? Your function could either be odd, or if it's not odd, it could be even, or it could be neither. Okay, don't forget about the neither. In fact, in many ways, the neithers are your most common. Okay, this one happens to be odd, and because it's odd and you're symmetric on either side of the the y-axis, it's going to come up being 0 by the theorem we did earlier on the page. So f is an odd function, and because f is symmetric about the origin over this interval from minus pi halves to pi halves, you can apply theorem 416 to conclude that this, the integral equidistance across the y-axis from minus something to the same positive of an odd function has got to be 0 without doing a single integration. But I knew y'all wanted to do an integration because that's how you told me to proceed, and that was fun to do anyway, wasn't it? But now we've, verified it. Any questions? Okay. From the graph of that one, which I didn't graph, and hopefully, if you wanted to do, well, let's see. Yeah, that's the graph. That looks an awful lot, but not quite, like just a regular old sine function. It isn't, because the sine function, you have the maximum that pi has, not your 0 that pi has. So it's not the sine function, but it looks a lot like one. The deal is, because it's an odd function, whatever is happening on the right, the opposite is happening on the left. And since you're integrating over a symmetric interval around the y-axis, whatever this is exactly negates what that is. That adds to 0. Make sense? All right. However, because one lies below the x-axis, the other lies above it, integration produces a cancellation effect, giving you a total area of 0, okay, if you think in terms of area. All right, that was the last slide, the last example in 4.5, which is in chapter 4. So here's your homework exercises. Do either 5 or 7. They're both at Calc Chat. 5's at Calc View. Do any of the odds 9 through 29. They're all at Calc Chat. 15's at Calc View. Do either 31 or 33. They're both at Calc Chat. 31's at Calc View. Do 35. That's a little different kind of problem, but we've done a few. They've had some like this before. That's at Calc Chat. There's a differential equation, which, frankly, seems like we shouldn't be doing those in this course, but we are. So that's 37. It's at Calc Chat. Then there's any of the odds 39 to 47. They're all at Calc Chat. 45's at Calc View. Either 49 or 51. They're both at Calc Chat. 49's at Calc View. Any of the odds 53 to 59. They're all at Calc Chat. 53's at Calc View. 61 through 67. They're all at Calc Chat. 65's at Calc View. Either 69 or 71. They're both at Calc Chat. 69's at Calc View. 73 or 75, they're both at Calc Chat. 73's at Calc View. 77 should be at Calc Chat. 79 should be at Calc Chat. You can explore doing 81 if you'd like. It should be at Calc Chat. 83 is a depreciation problem, which whenever you get to the point in your life where you have capital equipment, when it comes to income tax time, you can depreciate those capital assets, okay? So that's something maybe a little before your time, but you're going to be there one day. Get used to it, okay? 85 is a sales problem. 87 is a graphical analysis. 89 is rewriting integrals. All those should be at Calc Chat. 91 is a probability problem. That should be at Calc Chat. 93 through 97 are true false. They should be at Calc Chat. And Malcolm should be here. And he is here. Okay. And that's through 97. 99 is a rewriting an integral, and 101 is a proof if you're into that. Now, since this did finish Chapter 4, there's review exercises. So if you haven't had enough practice so far, you can do any of the odds 1 through 7. They should be at Calc Chat. 9 or 11 should be at Calc Chat. 13 should be at Calc Chat. 15 should be at Calc Chat. 17 at Calc Chat. Any of the odds 19 to 23 should be at Calc Chat. 25 should be at Calc Chat. 27, 29 or 31, 33, 35, 37, 39. Any of the odds 41 to 45, 47, either 49 or 51, 53, 55, 57, any of the odds 59 to 65, 67 to 71, 73, and or 75. Now, there's a problem-solving exercise also given. If you're into doing that, by all means take a look at it. You'll see there included is something about the Fresnel functions on question 5 of that. Even if you're not interested in doing the problem solving, that might give you an idea for a paper topic, folks. Hint, hint, okay? This, of course, is one of my best classes ever. I've received 3 research papers, and we have 1 weekend left. 1 class left, okay, before final exam. I need those papers in, and I need them in preferably today or tomorrow. Yes. I'll be giving you your final at the end of class today. We won't have covered all the material, but that enables you to get started over the weekend while you're working on your paper, okay? And then when we finish class on Monday, then anytime after the Monday, you can turn in the final. Yeah. Okay. I'm sorry?
Hey, did you open the door yet?
Oh, no, I didn't. If you want to walk through, you can.
Yeah, I got you.
Okay. Okay. Just open the door and don't close it back. I can't unlock it, but I can open it. Okay. I'm glad somebody's looking out for me. So anyway, Fresnel function. Who was Fresnel? How did he develop this function? Why did he develop this function? Who uses this function? There's lots of possibilities there, as well as plenty of others. Okay? So you can do anything in the problem solving there. There's also a number 19, another new function introduced, the sine integral function. And that's not named after anybody, but you may find that something interesting to look at, especially if there's some application that may pertain to you. All right. Any questions? Chapter 4. Okay. Let's get out of Chapter 4. 4.5 and move on to 5.1. All right. Chapter 5 is a very long chapter, okay? So we can't possibly do it in 2 days. But let's fly through as much as we can. I think I told y'all before, I like the author. I don't like the organization of this book. And he, as other authors have done, have rewritten this and incorporated what they call early transcendental functions into the regular chapters. That's what we'll be going to in the fall. If you're in Cal 2 or Cal 3, we'll still use this book. But If the students who are in Cal 1 in the fall, they will be in the new book, which is incorporates, and we won't have to do a separate Chapter 5 at the end. So, that's just a little housekeeping to let you know how fortunate you are. Or something like that. All right, so let's go. Current slide. We're going to hopefully go through 5.1 fairly quickly. Okay? And by the way, the name of the chapter is Logarithmic, Exponential, and Other Transcendental Functions. We're going to focus on logarithms and exponents. We'll probably mention a few of the others, but we're going to focus on these two. So 5.1 is the natural logarithmic function and how we go about differentiating it. Now, okay, our objectives here are to develop and use properties of the natural logarithmic function. We'll understand the definition of number e, which is in exponential functions, which should seem to be in the next section, but we'll incorporate it here, and we'll find derivatives of functions involving the natural logarithmic function. Now, they kind of drag this out in gory detail. I'm going to try to speed through it, but I don't do very many things rapidly well, so we'll get through it as we can. So let's look at the natural logarithmic function. Okay, let's do a flashback, okay? Remember how we integrated x to the n. What was the antiderivative of x to the n? Yes, exactly. It's x to the n plus 1 divided by n plus 1. Now, what's the only problem? There it is right there. Plus c. Okay, always have a plus c. What was the only condition for this? What do you have to watch out for? What can n not be? No. Negative 1. It could be 0. It could be 1. It can't be negative 1 because that makes your denominator 0. So the integral of x to the negative 1 dx does not follow this rule because you get an impossible answer. So n cannot be negative 1. That's your general power rule. What do we do if n is negative 1? Can we not integrate that? You have to have another rule. Exactly. This is an important disclaimer. It does not apply when n is negative 1. Consequently, you have yet to find an antiderivative for f of x equal 1 over x, which is the same as x to the minus 1. In this section, we'll use the second fundamental theorem of calculus to define such a function. This is sort of a long roundabout way to do it, but it's doable. It is neither algebraic nor trigonometric, but falls into a new class of functions called logarithmic functions. This particular function is called the natural logarithmic function. Here's its definition. The natural logarithmic function is defined, guess what? The log of x, ln of x. Now, are y'all familiar with logarithms at all? Okay. Say again? What's that? Okay. Now, probably not that. Okay. There are two types of logarithms, actually many types of logarithms. Two basic types. Natural logarithms and then any other base. Okay? Base 10 is the one we use a lot, but that's not the only. You could use any base. The natural logarithm is base e. And that's why we're going to talk about that a little later. But don't worry about that yet. So ln means natural logarithm. And here's the definition of the natural logarithm. Natural logarithm of x is the integral from 1 to x of that very thing we did not have defined, 1 over t dt. Okay, t to the minus 1. The power rule will not work with that one. Now, sort of another disclaimer here, x has to be greater than 0. Okay? Why? Because you wind up putting 0 in the denominator, you can't do that. Okay? And so then you'd have to choose one side or the other. Let's always go with the positive side. Now there's more reasons than that, but we'll get to those reasons later. So x can't be 0, so let's keep it always positive. Now that does create sort of an issue there. When x is less than 1, this is kind of backwards, isn't it? Because you'd have the smaller number on top and the larger number on the bottom. X greater than 1, this makes really good sense. Okay? So we'll see that as ramifications as well. The domain of the natural logarithmic function is a set of all positive real numbers. No negatives and not zero. Okay? They have to be positive. It's a lot like the square root function. Square root function could be zero, but it can't be negative. The natural log function can't even be zero, and certainly can't be negative. Okay? So, that's our definition of the natural logarithmic function. From that definition, you can see that log x is positive when x is greater than 1, negative when it's between 0 and 1. Okay? Now, the reason for that was what we were just talking about. If x is between 0 and 1, then this number is smaller than that one, so you'd have the negative of log x. In other words, a negative value. If x is greater than 1, this is going to be a positive value. What happens if x is equal to 1? Interval from 1 to 1. What's that? 0! Excellent, because it's infinitely thin, okay? Not me, but infinitely thin. The value there is 0. So any x less than 1 is negative. At 1, it's 0. And anything greater than 1 is positive. Okay? And you can only have x's greater than 0. So, moreover, and here's what we just said, log of 1 is 0 because the upper and lower limits are the same when x equals 1. So, here is the graph of y equal 1 over x. And if x is greater than 1, then this thing is positive. If x is between 0 and 1, because you're doing from the larger to the smaller, that's the opposite of the smaller to the larger. So this is a negative number back here. Of course, if it's equal to 1, the interval is 0. Okay? So log x is negative for when x is between 0 and 1, 0 at 1, positive when x is greater than 1. Now, if you sketch the graph of this log y is equal to log x, you can think of the natural logarithmic function as the antiderivative given by this differential equation. dy dx is equal to 1 over x. In other words, write that in differential form. dy is equal to 1 over x dx. Integrate this, you get y. Integrate that, you get log x. Okay? Well, if you think about dy dx as being a slope, when x is equal to 1, your slope is 1. There it is. Okay? And that's at 1, 0. When x is greater than 1, your slope is decreasing, but always positive. Okay? When x is between 0 and 1, then this number, your slope is then a very steep slope, always positive, and the closer you get to 0, the steeper it is. The closer you get to 1, the closer to 1 it is. Okay? So this is what your natural log function looks like. Okay? Now, figure 5.2 is a computer-generated graph called a slope field or direction field showing the small line segments where the slope is 1 over x. Y dx, which is the slope, first derivative, 1 over x. The graph of y is equal to log x is the solution that passes through the point 1, 0. Okay? So you line these up as well as you can so they go like that. That's how the log function looks. The value is negative anytime between 0 and 1, 0 at 1, and positive from the left. Now, this is beyond what we're talking about here. What good are logs anyway? Well, here's what they're good for. What if you had incredibly large numbers, such as astronomical distances, like the distance from the Earth to the moon, Earth to the sun. Okay, I know I had a pen here, so there it is. Jemiah is here. All right. Several people have come in since I made announcements at the beginning. I need to emphasize a couple of those again. So before we leave, before anybody leaves, give me a couple minutes to say to me, I got to go or blah, blah, blah. and then I'm going to make those announcements again because everybody does need to hear those. You may or may not go back and listen to the recording at the beginning of the class, so if you think you may not, be sure to ask me. So just reminded me, most of you were not here when I started class and made those announcements. So let's go on from here. So what do logs do for you? Say astronomical distance, like the distance from Earth to Sun, is approximately 93 million miles. That's 93,000,000,000. It's a pretty big number. If you took the log of that, you get a much more reasonable number. Okay? And so you can take either very small numbers or very large numbers and make them a more reasonable type number. Okay? To deal with. And many things, Kepler's laws of planetary motion depended on logarithms. If you did the log of the, if I can get it right, the cube of the distance or the speed or something like that, and compared it to the square of the other one, you get a straight line. Okay? Logs do that kind of stuff very, very nicely for you. Okay. I forgot to turn my page here. Okay. And by the way, the figure at on 5.1 in the margin, left-hand margin of the very first page, 314, is the drawing of John Napier. He was the inventor of logarithms. Okay? He was a Scottish mathematician, and if I am not terribly wrong, I believe he was a pastor. And you might say, wow, pastors got into math? Well, back at the time when he was around, basically the clergy were some of the most educated, if not only educated people in society. So it's not at all surprised that he was a pretty sharp dude. Okay? He coined the word logarithm from two Greek words, logos, and they use that as ratio. Okay? Now, I found that I've always heard of logos meaning word, but they are saying it's ratio, and arithmos, which is number, so logarithmon, okay, arithmon, log from log, logos, arithmos, logarithm, or number. He described the theory, spent 20 years developing, first appeared in a book, and that, by the way, is a Latin title, because back then, education was done in Latin. Even though no one spoke Latin, that's what the universities taught, and all scientific and any other kind of scholarly work was done in Latin. Okay? The description of the marvelous rule of logarithms is what those words stand for. He did not introduce the natural logarithm. He did the it says even though he didn't introduce it, sometimes it's called the Naperian logarithm. So Ln could be Naperian, even though he didn't do it. Most of the time that just stands for natural. So blah, blah, blah. Okay. This theorem lists some of the basic properties of the natural logarithmic function. The natural logarithmic function has the following properties. Okay? The domain is 0 to infinity. Domain. Not counting 0, that's a parenthesis there. Starting just beyond 0, going to positive infinity. We've already seen that in the graph. The range, however, goes from minus infinity to positive infinity. Okay? Reaches minus infinity between 0 and 1, or goes for it as you get closer to 0, and then as you get closer to positive infinity, the range goes to positive infinity. The function is continuous, always increasing, and therefore a one-to-one function. Always increasing meaning monotonic. The graph is concave downward. Okay? Go back and look at the graph one more time. Concave down. Okay? Never concave up. Always increasing, but concave down. So it's increasing at a decreasing rate. That's what concave down means for you. Okay? So those are the characteristics of the properties of natural logarithms. Okay? Now, using the definition of natural the natural logarithmic function, you can prove several important properties involving operations with natural logarithms. If you're already familiar with logarithms, you'll probably recognize these. Some of you may not. Okay? So, here's some of the logarithmic properties well worth knowing and remembering. If A and B are both positive numbers, okay, because you can't take the log of the negative numbers, so they have to be positive numbers. Can't be zero. They're positive numbers, and n is rational. Doesn't have to be an integer, any rational number. Then the following properties are true. Now, we've already hit this one. The natural log of 1 is 0. Always. Okay? Number 2. The log of a product is the sum of the logs. The log of a product is the sum of the logs. Now, you might ask yourself, why did Napier go to the trouble of coming up with these things? Well, Napier probably had run into difficulties in multiplying really big numbers. Now, remember, Napier was a little before calculators, okay? A lot before calculators. Everything was done by hand. And if you're multiplying 5,844,322 by 6,588,967,413, that's going to be a long process if you're doing that by hand, right? So Napier said there's got to be an easier way. He was a good mathematician, always trying to find an easier way to do the problem. And he came up with these things that change a multiplication problem into an addition problem. Now, I don't think a single one of you has lived a day of your life, even when you're an infant, when there wasn't a calculator available. Now, you couldn't use them when you were an infant, but they were still available, weren't they? Okay? I had a suspicion of that, but I can't guarantee it, but I suspect that. I, however, am a little bit older than you, and I was a sophomore in college, probably older than most of you are right now, when I saw my first calculator. And here's Demiria. She came in just for this story. Okay? I remember it well because it was fall term, I think. It could have been winter. I was in a big physics lecture room at Georgia Tech, probably close to 200 students in the room. 8 o'clock class, I think, because that's when I usually took physics. And most of us were already seated, waiting for the first day of class, and in walked these two guys that had strapped to their belt, believe it or not, that's what they did, these packages, and we'd all heard about them, but I had never seen one before, a calculator, okay? Now, the rest of us that were in that room, most of us had strapped to our belt, believe it or not, that's how you carried them, what is called a slide rule. Has anyone ever even heard of a slide rule before? No. Okay. What a slide rule was, and you have various kinds, but basically it's a ruler-looking thing with a scale on the top and bottom, and then the middle scale slides in between. Okay? What's that? You have seen one before. Okay? Why did you have these? When you were multiplying very large numbers. John Napier came to our rescue because you put the first number in, it was in a log scale, find the first number, at least to the first maybe 3 significant digits, find that on the base scale, slide that middle one over to that, so the 0 lined up there, find the second number to this, you added the log of this one plus the log of that one without even realizing that you were doing it, and then you took the anti-log of your answer, and that was the product. It was a lot easier than multiplying huge numbers. Okay? So there it is. Log of a product is the sum of the logs. Carrying that yet another step, what if you had the product a times a times a times a times a times a times a, that's to the nth power? Well, that would be a plus log 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 a, because these are multiplied. You add those, that's n times log a. So now you're able to deal with powers very quickly and easily, having to note antilogs. But yeah, that's how we did it. That's how we raised big numbers to fairly large powers. You did it with a logarithm. Okay? Following up on this one, if the log of a product is the sum of logarithms, the log of a quotient, so you can do division really easily. Not exactly, not precisely, but at least close enough. And that's the difference of the logs. The log of A minus the log of B. Why? Because this is log of A times minus B to the minus 1. And sure enough, that's what comes up here. I've jumped a rabbit there, but it's still true. Now, so what did the other 198 of us sitting in the classroom do when we saw those two people come in with those calculators? We went, oh, there goes the curve, okay? Because all we could do was get approximate answers. They can get pretty close to exact answers. Now, let me tell you a little bit about those calculators. They could add, they could subtract, they could multiply, they could divide. They couldn't do any of the other functions yet. Oh, and they cost about $400. Oh, and you had to plug them into the wall for them to work. So they had to sit near plugs, or their calculators were worthless to them. And we all took up the seats near the plug. No, we didn't do that, did we? No, we wouldn't have thought of doing that, did we? Okay. So that was my advent into modern technology. Never mind. All right. So what would that be? Log of 10 divided by 9. Just give me another way to write it. Log 10 minus log of 9, that's property number 4. Okay? And if you have a calculator, you could do it that way. See that you do get the same answer. Okay? How about this one? Oh, my goodness, what in the world is that one? What would you do first?
Change it to 3x plus 2 to the 1/2.
Ah, write it in exponential notation. Good. And what would that be?
1/2 log of 3x plus 2.
Perfect. Okay. Well, they didn't do it. Okay, but we'll see they do it next. And then we'll do this as 1/2 the log of this. And we almost have to stop there. So it's 1/2 the log of 3x plus 2. Okay. Now they have left off something here, but it's okay for them to do here. And what this is, and they really should have done it at this step as well, maybe even at that step. You have to understand 3x plus 2 cannot be negative, can it? Because you can't take the square root of a negative number. So they really should have that in absolute value bars, which then they should do this in absolute value bars with 1/2 there, or this, and that should be absolute value bars, because not only can you not take the square root of a negative number, you can't take the log of a negative number either. So a lot of times you'll see when they have an expression following a log, they'll put absolute values, so you can't do a negative number. But they're not doing that yet. Okay? How about this one? What in the world would that become?
Log of 6x minus log of 5.
Perfect. And how about that 6x?
Log of 6 plus log of x.
Oh, they didn't do that. Not here. They'll do it in the next step. That would be log of 6 plus log of x minus log of 5. Perfect. Okay. Now, did we forget to take this another step? No. There is no rule for a log of a sum. There is no rule. Don't make up a new rule for a log of the sum. The logs of products and quotients and powers and roots, yeah, those have rules. You can't do, there's no rule for a log of the sum or the difference. The log of a product is the sum of the logs. The log of a quotient is the difference in the logs, but there is no rule for logs of sum or differences. Those are already as simple as you can get. You can't go any further. Okay. Now, this, oh my goodness, what would that be? Anybody?
You can write it as the log of the numerator minus the log of the denominator.
Okay, log of the numerator, which would be x squared plus 3 squared, divided or minus the log of x to the cube root of x squared plus 1. And that's what they get. The log of the numerator minus the log of the denominator.
So the whole function, the whole denominator would be a negative exponent?
Yeah, well, you put the minus in there. That's taking care of the negative exponents. Okay? Now, what can you do with this one?
Move the 2 in front.
Yes, move the 2 in front. That would be twice the log of x squared plus 3. Okay, what can you do with this one?
I guess turn the power to the exponential, the square root exponent.
Okay, you're going to do that at some point, but first I would take the product and write it as a sum. But it's preceded by a minus, so it would be minus the log of x, and if you put it in parentheses, plus, but if you don't put it in parentheses, minus the log of this. And then that I would put in parentheses. So let's see if they did it that way. They brought down the 2 here, 2 times the log of x squared plus 3, minus, and they put it in brackets here, the log of x plus the log of, and then they wrote this just as you suggested. They must have been listening to you. Write this in exponential notation, x squared plus 1 to the 1/3 power. Okay, there's 1 or 2 more steps to go. Is there anything else you can do here? Is there a rule for log of sums? No, don't even try it. Okay, that's all you can do to this one. How about this one? Well, you can distribute the minus sign across and make that minus log x, but this one you can do,
The 1/3 to the
yeah, 1/3 of the front plus 1/3 log of x squared plus 1. But then if you distribute that, that becomes a minus. So let's see what they do. Yeah, they do both. Well, no, they only do one. They first distribute the minus sign across and make both of those minus. Now they got that last step to do, bring the 1/3 down in front. So 2 log x squared plus 3 minus log x minus 1/3 log of x squared plus 1. What do we do with this one? Nothing, absolutely nothing. There is no rule for logs of sums. Only logs of products, quotients, and powers, which includes roots. Does that make sense? All right. Made enough sense for Jalen to get it done. That's good. All right. So again, remind me before anyone has to leave, give me a couple of minutes so I can go over end of term information. Okay. Second? Oh, okay. When using the properties of logarithms to rewrite logarithmic functions, you must check to see whether the domain of the rewritten function is the same as the domain of the original. Now, this is a little tedious here, but it is true. For instance, the domain of f of x is equal to log of x squared. Okay? What would be the domain of that function there? What values could x take on? All real numbers. Because if x is negative, x squared is positive, you can take the log of a positive number. If x squared is positive, if x is positive, x squared is positive, you can take the log of any positive number. The only thing you can't take is 0. X cannot equal 0. So it can be any positive number, any negative numbers. It can't be all real numbers because you have to exclude 0. But if you do the rules for logarithms, say 2 times log x, now what can x be? Positive only, because you can't take the log of a negative number. So here you could take the log, x could be negative. It can't be 0, but it could be negative. Down here it can. So when you use these rules, it may change your domains. Okay? So you have to watch for that. You can't put a minus x in here. You could put a negative value for x in here, because you square it, it becomes positive, you can take the log of it. Here you can't put a negative x in there, a negative value for x. Okay. Let's see. We did example 1. So now we're ready for the number e. Now, did y'all realize e was a number? We think of e to the x or something like that. Well, e is just a number. It's a base. And it's a very special number. One of my favorite numbers of all time, okay? It is likely you have studied logarithms in an algebra course. I don't know if you have or not. Hopefully you have. There, without the benefit of calculus, logarithms have been defined in terms of a base number. Okay? That's why I said e is a base. For example, common logarithms have a base of 10. And if we don't write the 10, if they say log, you assume it's a 10. And the log base 10 of 10 would be 1. Why is that? Because use the base, raised to what power gives you that number? And that would be the first power. The base for the natural logarithm is defined using the fact that the natural logarithmic function is continuous, is one-to-one, and has a range from minus infinity to infinity. Okay? Continuous, one-to-one, and has a range of minus infinity to infinity. Now that sounds like that could do for lots of things, but let's see what they're talking about. So there must be a unique real number x such that log x is equal to 1. Okay? Because, it's a continuous function. It's one-to-one function. There's got to be some number there, because log of a negative number, log of something between 0 and 1 is going to be negative. Log of 1 will be 0. And log of anything above that is going to be positive. So there's got to be some number x that the log of x is equal to 1. Okay? Now here's what your y is equal to 1 over t. And the area of this would be the integral from 1 to x of 1 over t dt. And when this area is exactly equal to 1, there's got to be some number out there that makes that area exactly 1. Okay? That number is denoted by the letter E. Why didn't they just give it a number? What's the area of a circle? Yeah, radius is involved. What's the area of a circle? Anyone know? How about the circumference of a circle? Anyone know that?
Denominator, radius times 2.
Okay. No, the diameter is radius times 2. What's the distance around the circle? Circumference of the circle. Okay, 2 pi r. Perfect answer. Pi d, another perfect answer. What's pi? A number. Why didn't you write the number down? Why did you call it pi? It's an impossibly long number. It's an irrational number. Pi is an irrational number. We usually abbreviate it to be 3.14 or 3.1416 or 3.1415. You can go on and on and on. Never repeats itself. That means it's irrational and it goes forever. Okay? So yeah, it's too long a number to write. Well, guess what? E is a lot like pi. It's not the same as pi. It's a number, but it's irrational. So even though it's the natural base of our number system, it's an irrational number. Okay? can be shown that E is irrational, has nothing to do with gender, by the way, okay, and has the following decimal approximation. This is just an approximation, okay? Approximately equal to 2.718281828. Oh, it looks like it may have a repeating pattern. No, it doesn't. 4, 6, blah, 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 blah. It never repeats again. This makes it look like it's going to have a repeating pattern. It doesn't. After that second time, it never shows up again, I don't think. Okay. So that's approximately what E is. Like pi is approximately 3.14159. It just keeps on going. This is 2.718281882846, blah, 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 blah. Okay. Now, most of the time, I kind of round it to about 2.7. 2.72 would be a little bit more precise, but 2.7 is a good round approximation, like 3.14, okay? Nice approximation, okay? It is a number. It is a base. And it's the base that your logarithm is based on. So here's your definition of E. The letter E denotes a positive real number such that the log of E is equal to the integral from 1 to E. This is how we define log of X is integral 1 to X, 1 over T dt. And that integral is exactly equal to 1. That's what E is. Okay? Once you know that log E is equal to 1, you can use logarithmic properties to evaluate the natural logarithms of several other numbers. Okay? For example, by using this property here, the log of E to the n, what would that be? Log of E to the n. We just did it a little while ago. N times the log of E, right? But what's the log of E? 1. So that would just be n. Okay? That's sort of nifty, isn't it? You can evaluate log E to the n. That's just going to be n. For various values of n, as shown in the table, when x is equal to 1 over e cubed, which is approximately 0.5050, and 1 over e squared, 1 over e, so this would be e to the minus 3, e to the minus 2, e to the minus 1, e to the 0 is 1, the log of 1 is 0, okay? You can approximate these, and you can do the graph here. And sure enough, you get the log function. Those are pretty simple once you do it in terms of E. Okay? Of course, you have to evaluate what that E is. Now, if any of you ever need to know E, pull out your calculator, find the E to the X key, and put a 1 in there, press the key, or press that key and do a 1, and it'll give you 2.71828, blah, 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 blah. The logarithms shown in the table are convenient because the X values are integral powers of E. Most logarithmic expressions, however, best evaluated with a calculator. You have an ln key. Now, you probably have an log key too. Be careful. Log is usually common logarithms. Ln key is your natural logarithms. Okay. Joy's here. Okay. All right. And again, remind me before anyone has to leave, give me enough time to make all the announcements I made at the beginning before hardly anybody was here. Okay, 3 people were here. Okay. So pull out your calculators. What the log of 2? Ln of 2. 0.693? Yeah, perfect. Okay? What's the log of 32? Say again? 3.466 or whatever. Okay? Now notice here. Here the number 2 was your input. The output's a decimal number. Here your input is 32. Your output is something between 3 and between 1 and 10. This is between, the input's between 1 and 10, the output's between 0 and 1, okay? Input between 10 and 100, your output between 0 and 10, okay? So basically, you've taken big numbers and assigned a smaller number to it, okay? How about this one? The log of 0.1. Negative, because it's less than 1, 2.303. Hey, it worked all right when they were positive numbers. You get smaller numbers here when you have numbers, when you have numbers greater than 1. When you have numbers between 0 and 1, they can get small really quickly. So this actually becomes a bigger number here. So you lose that benefit of logarithms when you're between 0 and 1. Okay? Now let's talk about the derivative of a natural logarithm. Okay? Top of page 318, by the way. The derivative of a natural logarithm is given in theorem 5.3, that's coming up. The first part of the theorem follows from the definition of the natural logarithmic function as an antiderivative. The second part of the theorem is simply the chain rule version of the first part. So here is, let u be a differentiable function of x. So u is some function of x, and you can take a derivative of it. So d by dx of log x, remember how we defined it? Log x was defined as an integral when you take the integral, and it's the integral of 1 over x. Well, take a derivative of the integral, and you get 1 over x. There it is. Derivative of a log is 1 over whatever the argument of the log is. Okay? That's only good for x greater than 0, because x is not defined at 0, and x is not defined at negative. Only positive x's. Now, d by dx of log u, this is where we use the chain rule, it's 1 over u, because whatever follows the log, 1 over that, then times the derivative of this, du dx. So that would then be u prime du dx over u. Whew, that's nice, isn't it? So the derivative of the log is 1 over whatever the argument is. If the argument's a function, then you do it times the derivative of that function. Chain rule. Again, u has to be greater than 0. So there's the derivative of the natural log. So let's do that. What's the derivative of log 2x? Help me. Derivative of log 2x. Somebody help me. What does it mean? Derivative of a log. You need to know this, folks. Derivative of a log? Help me. Is that the Jeopardy thing? All right. What's the derivative of a log? 1 over 2x, then times chain rule times 2. Okay? So it's 1 over 2x. 1 over 2x times 2. The 2's go out, and you're back to 1 over x. Ooh, wow, that's amazing, isn't it? That doesn't seem fair, does it? But let's think about this. Okay? I'm going to do this another way. Okay? And you tell me if this is legal in most states. Okay? Let me get my pen back. Okay? D by dx. What's another way to write log of 2x? Anybody? We just did those properties. Second? No, that would be 2x. That would be x squared. The log of a product is the... Yes, that's the log of 2 plus the log of x. Correct? Yeah, Okay? Now, let's do this. What's the log of 2? What's the derivative of log 2? Guess what? Log 2 is just a number. What's the derivative of a number? Derivative of a number? 0. So this would be 0 plus derivative of log x would be 1 over x. Yes, that's right. And it is fair, okay? So that's doing it the short way, the direct way, but you could also do it this way. You get the same answer. Make sense? Yea or nay? Can I erase? Okay. All right. Let's do the B one. Okay. Cool. I don't have to cover anything on this one. All right. What's the derivative? D by dx of log of x squared plus 1. You tell me. Anybody? Help me. Derivative of log. Anybody? All right, here's Ashley. Okay, I heard someone say something, but I was saying here's Ashley. What do you say? Help me. Yes. Derivative of log is 1 over whatever the argument is. 1 over x squared plus 1. But then you got one more step, and what's that? The chain rule, okay. What would that part be? Derivative of the inside. What's the derivative of the inside? 2x. There it is. It's 1 over x squared plus 1 times the derivative of the inside, 2x. Let's see where they write that. Ooh, okay. So I'm going to erase my stuff. They write it as u prime over u, which is correct, but I like to do it 1 over that times the derivative of that, which is exactly the same thing. And your u there is the inside, which is x squared plus 1. The derivative of that is 2x. And then 1 over u would be 1 over x squared plus 1. So if you like doing it that way, perfectly fine. It's basically like doing a substitution. Okay? Good deal. All right, how about the C part? What would that be? Derivative of x log x. Guess what rule we need to use? Anybody? Product rule. How does the product rule go? Say again? You may have said right, I just can't hear well. Help me, somebody. How does the product rule go? Oh, how quickly we forget. Say again? Well, just tell me what any product would be. You got two functions here. The derivative of two functions would be? Okay, your first function, f of x. So that's just going to be x. And then the derivative of log x is? What's the derivative of log x? 1 over x. Okay, that's going to be pretty easy. Plus the first one, what's the derivative of x? 1 times the second, log x. So this will be 1 plus log x. Yes, you knew how to do that. Okay? That's it. No chain rule involved here, but it's a product rule. Say again? I can't hear you. Okay, about what? Okay. This is a product of two functions. The derivative of a product is the first times the derivative of the second. That would be x times the derivative of log x, which is 1 over x. That gives you this one. Plus the second times the derivative of the first. That would be log x times 1. And then x over x is 1. 1 plus log x. Okay? All right. The product rule hasn't changed. You're just applying it to a new function. So let's clear that and see how they did it. Oh boy, does that ever look pretty. Okay, it's the first times the derivative of the second plus the second times the derivative of the first. Okay, so the first is x times the derivative of log x is 1 over x plus the second, which is log x, times the derivative of x, which is 1. That would be 1 plus log x. Yes. See how it works? Any questions? All right. Is there a D? Yeah, there's a D. How would that one work? How would that one work? They're pulling out all stops here, aren't they? Say that one more time. It's the what? You're going to use the chain rule. You're absolutely right. And what would you do for that one? Say again? Okay, and what do you mean by that? I can... Say again? 3 times the log of x to the second power. Exactly. This is a power rule problem. Then times the derivative of the inside, which is 1 over x. Perfect. Way to go, team. That would be 3 log x squared over x. Perfect. 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 Let's see how they did it. Hopefully they did it right, too. Okay, let's see. All right, 3 times the log of x squared times the derivative of log of x. And that would be 3 times the log of x squared times 1 over x. Oh, and they just left it like that. Okay, that's okay. I would have put it over x, but they left it as times 1 over x. That's fine. Perfectly good, fine. All right, that was example 3. All right. Whoa, we've gone past our usual break time, haven't we? Do we need a break? Yay or nay? Does anyone need a break? I could use one, but I don't have to have it. Say again? Have a break? Is that what you said? Okay. So let's do a quick break here before we move to example 4, which will be this one. So, all right, to pause. There's actually 2 reasons I need to know this. One of them's for your benefit, and, well, both of them for your benefit. All right. The first of these is that I do have your test 4 ready, so I wanted to give it to you before you leave today. That's why I need to know if you're leaving for a break. Otherwise, you're not going to have the weekend to work on it, okay? So, if anyone's leaving, let me know so I can give you your test before you go. The second thing, though, and this is sort of a bigger issue, is that Monday, next day of class, I will be returning all of your tests back to you. I've already returned test 1 because everybody had done it. It seems like one person wasn't here the day I did it. So if you haven't got test 1, get it from me. Test 2, however, I think there's one person who hasn't turned in test 2. I don't believe that person's here right today. So I can't return test 2 to you. It's coming back to you on Monday. Test 3, there's probably 4 or 5 of you haven't turned in test 3. They have to be turned in by Monday because they're coming back. And if you haven't turned it in by the time I turn it back, that's a big fat 0. So please get your test 2 and 3 in by Monday because they're coming back. Yes? all that's been turned in have been graded so far. Yeah. Your papers I can't return to you. They've been graded too. The miserable little 3 of them that have been turned in have been graded. Okay. Those are also due Monday. Okay. Anytime after Monday, you start losing points. Okay. So I will be giving you your test, your Chapter 4 test at the end of class today. And it's not due until technically Wednesday. That's why I want to give it to you today so you have at least a week to work on it. But I will accept it on Thursday as well. Okay? So let me, just for funsies, tell you my office hours for the rest of the term. Today, I had office hours 8 to 8:30. I will have office hours 5:30 to 6. Same thing's going to be true Monday. 8 to 8:30, 5:30 to 6. Tomorrow and Tuesday, my office hours will be 8 to 8:30, 10:45 until 4:15. That's on this campus. And then at 4:15, I'll leave to go to the Birmingham East Campus for a physics class. So I'll be over there from 5 to 6:30. Okay? So you could bring me things over there 5 to 6:30 if you wanted to. Okay. Now, Wednesday, that's technically the first day of finals. We're not having class, but I will be here from 8 till 6. Oh, no, I won't. Wait, let me back up. They've called a meeting for 1 o'clock over on the Birmingham West Campus. So I'll be on this campus from 8 until 12:30, because I have to leave by 12:30 to be there by 1. And then after, the meeting will probably go about 2 hours, I'm guessing. I'm hoping it won't be any longer. So I'll be in a meeting from 1 to 3. If you want to turn it in on the Birmingham campus anytime after 12:30, you can do so. Go to room 122, and if Miss Saxon's in there, she'll take it and she'll give it to me when I show back up. Or if the meeting's over, I'll be in 122, and I will grade it. I'll take your papers then. But I'll be there the rest of the day from around 3 to 6. Okay. That's Wednesday. Thursday, I'll be on this campus from 8 o'clock in the morning until 4:25, maybe 4 o'clock, 4 to 4:15, something like that. And then I'll be going to the Birmingham campus, Birmingham East campus. So now, here's the deal. Technically, your finals due in by Wednesday. I will accept it Thursday, but if you don't get it to me on Thursday, I may not see it to grade it until after, because I'm hoping to be able to leave town Thursday evening, and I'll be leaving town from the Birmingham East Campus. So if you don't get it to me by, say, 4 o'clock on Thursday, you're going to have to get it to me over there, or else I won't see it until I come back for fall term. So that means you'll be getting an incomplete until I get to grade your paper. So that's the only bugaboo there. Yes? Okay. Yeah, Monday's the last day of class. Wednesday is technically when the finals due, but I will accept it Thursday. Okay, Wednesday, because they called that meeting, I will be here only from 8 till around 12:30. And then I'll be on the Birmingham campus from, say, 1 to 6. But I'll be in the meeting about 1 to 3 or however long that lasts. Okay. But I will be coming back to this campus on Thursday. So if you don't get it to me before I leave to go to Birmingham, and this campus is more convenient for you than Birmingham, if that's the case, then you can slide it under my door. And I'll pick it up Thursday morning. Okay? And I'll grade it Thursday morning. And I'll get your grades over. Okay? Oh, and that leads to one other issue. I'm way behind on putting grades on Blackboard, but you see, finally all the other distractions, except for that meeting on Wednesday, are over with, so I'm going to be grading and getting grades on Blackboard. All your stuff is graded now. I just haven't put it on Blackboard yet because I haven't had a chance. But starting tomorrow, when I don't have to go back to the Birmingham campus in the middle of the afternoon, I hope to be able to continue grading and get your grades on Blackboard. Okay? All right. So research papers are due Monday. Tests 2 and 3 are due Monday. you'll be getting test 2 and 3 back on Monday, and I'll giving you your test before you leave today, so you can start working on it. You may not be able to finish it before Monday, but at least after class on Monday, you'll be able to finish it then. Okay? Get it to me before I leave campus on Thursday. I'll leave campus on this campus at 4 o'clock on Thursday. I'll leave from the Birmingham campus around 6:30 on Thursday. So if you want to take it over there, you can. On Thursday, I'll be on the East Campus, the Ethel Hall Nursing Building, in room 214, upstairs in room 214. So if you don't get it to me before I leave this campus, get it to me over there. Okay? Any questions? About what?
About paper.
Paper.
So, what is it about again? I forgot what you said. Like, what's the topic about paper again?
You get to choose your own topic.
Okay.
Is that what your question was? Yeah. Has to do something with calculus. Okay? We've run across many names, many theorems, many formulas, applications, anything you want to write. Okay? Okay?
2 pages, right?
1 to 2 pages.
Oh,
Okay.
One page.
Anything less than 1 page, you're going to lose points. You won't lose points for being more than 2. Okay?
So 1 page.
Okay. Now, and let's go over again what a page is. Okay? If you have a header or other things like this, and then the title, and you triple space, you finally start typing right here. What's 1 page of text? It's going to go to the bottom of this page, and then on the second piece of paper, go at least that far. That's a page of text. So it's going to be at least 2 pieces of paper. At least 2 pieces of paper, but at least 1 page of text. Now, in addition to that, remember, I need a page from one of your sources. Okay, so if it's a book or something like that, can't be this book. And a works cited page too. Now, yeah, that's fine. So it may be 4 pages, okay? But it's 1 page of text, at least 1 page of text. Anything less than a page of text, you lose points. I do hold it up to the light and make sure that goes good. I do that. I promise I will. Okay. All right. Good question. Any others? Does that answer yours? Okay. Good deal.
I have a question for you.
You have what?
I have a question.
Okay.
What's your preference, MLA or AP?
I don't care. But what you need to be is consistent. So whatever format you choose, stay with it. Okay? If you start flipping and flopping and changing your format in the middle of the paper, you lose points. Okay? So you choose and be consistent. I don't care which one you choose, but stay with it. Good questions. Any others? And by the way, many of these questions should have been asked at the very first of the term. And then you could have been working on your paper all term. And you wouldn't be waiting till the last day to turn it in. Okay. But it's better to ask than not to ask. Okay. Any other questions? All right. Ready for the break now? All right. What's that? Okay. All right. Now, based on what we've done up till now, you may have begun to see a few possibilities. Rather than just making multiplication, division, and powers a little bit easier to do, there are other reasons a logarithmic function still has importance. On occasion, it is convenient to use logarithms as aids in differentiating non-logarithmic functions, okay? Because it can simplify things. This procedure is called the logarithmic differentiation. What a nice word. Okay. So here's one. Find the derivative of this, okay? What rule would you use?
I would change it to a multiplication problem using the product.
Okay, so you're going to first take the log of y? Not a bad idea. Not a bad idea at all. Lucked into it, didn't you? Okay, I'm sorry, I backed into it. Okay. So, yeah. Oh, I'm sorry, you're right. Let's back up a moment here. They skipped 4 and 5, so let's us do 4 and 5. All right, thank you. Differentiate this. F of x is equal to the log of the square root of x plus 1. We want to find f prime. What would f prime be? You want to do anything first? Second? Okay, so what would that be? Log of x plus 1 to the 1/2 power, and that would also be 1/2 times the log of x plus 1. Now, I'm always tempted to write absolute values there. The book's not yet, so I'll leave it as parentheses. Okay? Now let's take the derivative of that. And what would that be? What would that be? Anybody?
1 over x plus 1.
Okay, you're certainly going to have a 1 over x plus 1. Okay? Is that all, though? Okay, the 1/2 has to be included in that because that's a constant multiplier, and you do that first. So this is the same as 1 over 2 times x plus 1, which you could write, you don't have to, as 1 over 2x plus 2. I don't know how the book leaves it. Let's see. They leave it this way. Okay? And that's fine. That's perfectly good. Good deal. Okay. All right. Now let's do example 5. All right to erase? Okay. Example 5. Top of page 319. Differentiate this. F of x is equal to the log of x times x squared plus 1 squared over the square root of 2x cubed minus 1. Differentiate that. Anything you want to do first? Second? Okay, you want to do something with the log before you start differentiating? Good idea. What would you do?
Well, we'll subtract log of that.
Okay, so let's just write down the log of the numerator, which is the log of x, second, plus 2 times the okay, you want to back up and take it a few more steps? No? Yes? Okay, let's back up a bit. Okay. Okay. All right. How far back you want to go? Let's do it this way. Let's take it all the way back. Log of x times x squared plus 1 squared minus the log of, now, you want to do something to that denominator before I write it down.
Yeah.
What will you do? 2x cubed minus 1 to the 1/2 power. I like that. Okay? Now, this numerator, let's split that into 2 pieces. What would that be? Log of x plus, second? Did you say 2? I couldn't hear. Okay, yeah. Plus 2 times the log of x squared plus 1, okay, minus 1/2 the log of, okay, 2x cubed minus 1. Is that what I heard? Okay, so what you did, you took that logarithm we had and used the principles and properties of logarithm to expand it out to get it in a little bit simpler looking form. Question or just stretch? Okay, what is it?
What are you going to do with the 2 in front or behind the logarithm?
Okay. Good question. And that's why I asked if we're going to do it in one step or two. Texas 2 steps. Oh. Yeah, forgot that square there. Okay, now, you got the first part. Okay, you got the first part by doing log of the numerator minus log of the denominator, right? Okay, and you also were okay with rewriting the denominator as that, right? Yeah, okay. Now, this is a product, so that's going to be a sum of two logs, the log of the first plus the log of the second. So we could have written the step in here plus the log of x squared plus 1 squared. But I believe Tarika wanted to go and take the 2 in front. Okay? And that's the one you were asking about?
Yeah, I was just saying,
Yeah.
when are you going to put the 2 in front or when are you going to put 2 behind the logarithm?
Okay. Well, I don't think we ever put it behind, but we could put it in the denominator, as in here, when it's the exponent is 1/2.
No, I'm just saying, like, sometimes.
Oh, you mean where you write it? Okay, that's a good question. If you write it out here, then it's uncertain whether the 2 is multiplied by this or the 2 is multiplied here. So I always put it in front to remove ambiguity. Okay? Otherwise, you got to put something in parentheses so you know that's a unit. So if you put it in front, that removes the uncertainty.
So you said always put it in front.
I do. Yeah, it's not required, but I usually do that for that reason. Okay? That's a very good point. So now all we've done is rewrite the function. We haven't taken its derivative yet. So this is still f of x. Now we want to differentiate and do f prime of x. And what would that be? Anybody? 1 over x, is that what I heard? Plus 2 over x squared plus 1.
Minus.
Wait, not yet. Still got a chain rule to do, don't you? Times the 2x, okay? Now let's go to the minus 1/2. Times what? 6x squared. Perfect. Now all that's left is to do a little bit of cleanup. Okay? You're the cleanup hitter, right? Okay, never mind. Okay? The 1 over x is by itself, so leave it alone. Plus, well, you can multiply the 2 by 2x. That'd be 4x over x squared plus 1 minus. Okay, now here you could do 2 in the 6 and make that a 3 there. And that would be a 3x squared over 2x cubed minus 1. I think that's as simple as you can get it. I see no reason to try to get it over a least common denominator or anything like that. That's just a lot of extra work. So let's see if that's how they leave it. 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Perfect. Okay. Good deal. Now, we're ready for example 6. So now we would get to the place where we do this. Talk about procedure called logarithmic differentiation. Okay? That's what example 6 is. Now, I'm real tempted to say this first, so I think I will. Okay? So find the derivative of this, So what are we looking for? We're looking for y prime. Everybody agree with that? Just tell me. That's what we mean. That's what we're looking for, right? Find the derivative of y, that would be y prime, right? Now here's an observation, and tell me if I'm right on this. What if we did the log of y, okay, and that would be equal to something. I'm not going to go into what it is yet. Then what if we took the derivative of that? What is the derivative of log y? It would be 1 over y times derivative of y, wouldn't it? Well, this is the thing we're looking for. So what we do, once we figure out what the log of y is, then multiply that by y, and we've got y prime. And that makes the whole process simpler. What's that? Whatever I said, okay? All right, give me $100. No, never mind, I didn't say that. Okay. All right. Not just kidding. Okay, sort of. Okay. So what we're going to do is, as I think you suggested a while before, let's first do what the log of y is. Okay? You said that back before we were doing this. So first thing, we were looking for this, but let's first do this. Figure out what log of y is. Now, time out just a moment. Why in the world did they say this? Yeah, the whole thing's equal to 0, and can you take the log of 0? No. Okay, that was why they said that. Has nothing to do with the denominator here, has to do with the numerator. So if x were equal to 2, this step doesn't work. Okay? But if x is not equal to 2, you can do this legally in most states. So let's first take the log of y, and what would that be? Anybody? Second? I still couldn't hear. Okay, now where did you? Yeah, the log of y. Not the derivative of log of y, but the log of y. There's y, take the log of it. We were just doing things like this. What would that be? Anybody? What would be the log of y? Is what? Okay, no. Well, I'm not taking the derivative of log y. That would be that. I want to know what log y would be. What would that be? I mean, we're just doing this type of thing before. Log of the numerator, which would be x minus 2 squared minus the log of the denominator. Do you want to rewrite that? How? X squared plus 1 to the 1/2 power. Okay. There's the first step. Let's continue. Next step would be okay, so that would be 2 times the log of x minus 2 next minus 1/2 1 over x squared plus 1. Oh, why did I do that? Duh! That's terrible. Where did that come from? Okay. Ryan made me do that. Okay. X squared plus 1. No. Log of x squared plus 1. The old gray cells are falling apart here. Okay. So now we've done the log of y. Now what might we do? We're looking for y prime. we got off distracted here and did the log of y. But what can we do next? Now let's take the derivative of log y. D by dx of log y. And what would that be? This is what you were answering before. Y prime over y. Remember? The derivative of log y would be 1 over y times y prime, right? So let's take the derivative of this side too. What would that be? 2 times 1 over x, 2 over x minus 2. Okay, got it. Next. Next. 1/2. 2x over x squared plus 1. Very good. Did 2 steps at once there. The derivative of log is 1 over this, and then the chain rule part was the 2x. So put that on top. So there you got y times, that's y prime times y. So what y prime is just multiply y by that mess. I mean, that stuff. So this will be, I'm going to do it down here just because I've got more room. That would be 2 over x minus 2 minus, and here, by the way, the 2's can go out, and you have left with x over x squared plus 1. There's the first half. Multiply that by your y, and your y is x minus 2 squared over square root of x squared plus 1. Okay? Now, that is your y prime. It's this thing multiplied by y. Now, there's a little bit we could do to clean this up. For instance, when we multiply this by the first term here, one of the x squared, x minus 2's will go away. So that would give you 2 times, because that denominator goes away. So what we're doing is distributing this across here. And that would give you 2 times x minus 2, because the denominator goes away, minus, now this one's not quite as pretty, but it's still doable. This would be x times x minus 2 squared. There's your numerator. Your denominator is now this to the 3/2 power, because this is a 2/2 plus 1/2 is 3/2. So I'm going to write this as x squared plus 1 to the 3/2 power. Now, it would be legal to then multiply this by this, expand it. I see no reason to do that. This, to me, is a fairly simple solution. So that's what your y prime is. Now, let's see how they left it. Oh, they didn't, did they? Why did they do that? But they did. I messed up too. This is over x squared plus 1 to the 1/2 power. Sorry about that. I multiplied the numerators, but I forgot to multiply by the denominator. So this is the 1/2 power. Well, that's a really ugly 1/2, but okay. That's even uglier. Okay. Let me see if I can make that look a little better. Okay. Okay. So now I think I will put it over least common denominator. Let's multiply numerator and the denominator by s squared plus 1. So you get 2 times x minus 2 times x squared plus 1 over this thing to the 3/2 power minus x times x minus 2 squared. All that is over x squared plus 1 to the 3/2 power. Now, there was absolutely Okay. Now, I know that they're doing a lot of manipulations with algebra, which is fine. But see what we did, we had this thing here, which is your y prime over y, and we multiply that by y to get y prime, okay? So that's what y prime is this thing here. Now we distribute this across here and there, and when you multiply this by this, your x minus 2 in the numerator goes out, and the denominator goes out. So you're left with 2 times x minus 2 times x squared plus 1 to the 1/2 power. I just rewrote it like this. When you multiply these two together, you get x times x minus 2 squared divided by this to the 3/2 power. Because this is to the 2 halves, that's the 1/2. Now, these two denominators are similar but not quite the same. To get this to be a 3/2, you have to multiply the numerator and the denominator by x squared plus 1. And that's what we did there. Now, this is the tricky part. Notice that the numerator has an x plus 2 in both terms there. So let's pull that out. So this is going, what I'm going to do, I hate to do it this way, but I'm going to erase this line because we've already used it. We don't really need it anymore. I'm going to write my answer right there. This is going to be, let's pull out an x minus 2 out of both terms there, and that leaves us 2 times x squared plus 1, which would be 2x squared plus 2, okay, minus x times x minus 2, so that would be minus x squared plus 2x. And this is over x squared plus 1 to the 3/2 power. Now, if you combine like terms in here, this gives you x minus 2 on the outside. On the inside, these two add to x squared plus 2x plus 2 over x squared plus 1 to the 3/2 power. Now, all we were doing there was just making it look better. This answer's perfectly correct. This answer's perfectly correct. That answer's perfectly correct. This answer's perfectly correct. That one's perfectly correct. It's just done a little bit simpler. And that's how they leave it in the book, I think. X minus 2 times x squared plus 2x plus 2 over x squared plus 1 to the 3/2 power. Okay? Except for being a little more concise and better looking, the answer is no better than the others. It's just a little bit. It's simpler. And we always like to get it as simple as possible, even when it's really complicated. Right? Okay, any questions on that? Let's see how they do it. And I bet you they're going to skip steps like crazy and you won't be able to tell what they were doing anyway. But I need to leave that up here a little bit longer. People still writing? Need to leave it longer? No? Okay. So let's clear this ink and let's see what they do. Now, note that y is greater than 0 for all x is not equal to 2. Because when x is equal to 2, y is 0. But anything other than x equal to, that's positive and that's positive. Okay? So the log of y is defined as long as x is not equal to 2. Okay? Now, begin by taking the natural logarithm of each side of that equation. So we're going to do the log of y and the log of the right-hand side as well. Okay? Then apply the logarithmic properties and differentiate implicitly, and then finally solve for y prime. Okay? So the first thing we're going to do, and I don't know why, but periodically it shows up with a vertical bar there. It means absolutely nothing. I don't know why it's there. It just shows up on the screen, and I don't know why. Okay? It's meaningless. It doesn't contribute to anything. That's just a restatement of the problem we have here, except they put a bar in front of it. Okay. So the first thing we're going to do, that's the original equation except for that bar, and we're going to take the log of both sides. The log of y is the log of that whole thing on the right. So that whole thing on the right, the log of y is equal to 2 times the log of x minus 2 minus 1/2 times the log of x squared plus 1. Just like we did, they did it in one step, we probably took 2 or 3. Okay? Now what we're going to do is take the log of both sides, take the derivative of both sides, and the derivative of log y would be 1 over y times y prime, chain rule, right? So that's what this is. Take the derivative here, and you get 2 times 1 over x minus 2 minus 1/2 times 1 over x squared plus 1 times 2x. So there we have our derivative. So what we're going to do now is multiply, well, let's see, we will simplify things where we can, and multiply both sides by y. Okay? So y over y prime. Okay, now they didn't do that. They went on and did their least common denominator now. Okay, that's perfectly fine. Okay? Least common denominator was x minus 2 times, they did cancel out the 2. They didn't show you that, but they did. So let me go on and show you that. Okay. The 2's go out there. Okay. Divided them out. And then this denominator is x minus 2. This denominator is x squared plus 1. So you take the 2 here, multiply it by that, you get 2x squared plus 2. That's that new numerator. Over here, multiply both sides by 2x minus 1, so that gives you minus x squared plus 2x. Now, they did several things there at once, and then you combine like terms. This was a 2x squared minus x squared. So they did all the math we did. They got it to this one. Okay? Then what they're going to do is multiply both sides by y. Okay? And they did that there. But then let's plug in what y actually is. That was your x minus 2 squared times the square root, divided by the square root of x squared plus 1. Okay. Now, that's a quotient. That's a quotient. Okay? These two quotients have this term in common, so we'll wipe out one of these and all of that. Okay? And what that will leave us with the x minus 2 up here times this thing up here. Down here we'll have the square root of this times that, which is this thing to the 3/2 power. So they do that. X minus 2 times this thing here divided by that to the 3/2 power. And that's your answer. Now, perhaps the way they did it skipped maybe a step or two than what we did, but you got the same answer. Just went about it just a little bit different. Okay. Does that make sense? All right. Because the natural logarithm is undefined for negative numbers, you will often encounter expressions in the form of, and this is what I was telling you earlier, log of absolute value of u. If we don't know the values of u, we put absolute value bars because you can't take the log if those are ever negative. So put absolute value to that. The next theorem states you can differentiate functions of that form as though the absolute value notation was not present. Okay? So if u is a differentiable function of x such that u is not equal to 0, it can't be 0 because you can't differentiate something that's not defined, and log of 0 is not defined. But you can if it's anything other than 0. Okay? Now, all this tells you is this still comes out being u prime over u. Okay? Now, we're not going to go into why that's the case, but if u were negative, okay, then u prime, there's a good chance it would be negative, and negative divided by negative is positive, so yeah, you don't need to worry with that. Just do it the same way we did it, just the absolute value bars one there. Okay? So that frees you up to do that without telling you really why. Okay? There is a little proof that follows that, and you're certainly welcome to look at it. It basically comes out the same thing I just said, but we'll go from there. So, let's see, do they do example 7? Yes, they do. So find the derivative of f of x equal log of absolute value cosine x. So what would f prime of x be? You tell me. Based on what we just did in that theorem right there. What would that be? What is the derivative of cosine x? Negative sine x over cosine x. Okay? Now, that's it. You don't have to worry about absolute values or anything else. That's it. Let's see how they did it. I think it'll be the same way because it's that simple. Using the theorem, that would be u prime over u. That would be minus sine over cosine, just like you did, which is negative tangent. Okay, we did do that. Yeah, it's negative tangent x. Okay, sorry about that. I forgot to simplify. Any questions? Okay. Now that's the last slide. However, it's not the last example. There is an example 8. Finding relative extrema. Locate the relative extrema of y is equal to log of x squared plus 2x plus 3. We want the relative extrema of that function. How do we find extrema? Think maximum or minimum. How do we find them? Take a derivative. Good answer. So y prime is equal to what? Second? A little louder. 2x plus 2 over x squared plus 2x plus 3. Okay? Now, we took a derivative. Why? We're looking for local extrema. What does your derivative have to do with your local extrema? Okay, and how do you do that? Yes, set the derivative equal to 0 or where it doesn't exist. Okay? Now there may be a value somewhere here where it doesn't exist, but I don't think so. Not in the real number system, because if you were to try to set the denominator equal 0, which would be where it doesn't exist, I think you'll find this an irrational number. I mean, not irrational, non-real number. Okay, imaginary number. So, where it's equal to 0 is where? X equal what? Okay, it's equal to 0. Let me write this better. I'm writing what you're saying, but it's not necessarily making sense. First thing you do is set it equal to 0, and that will be at the place where x equal negative 1. So that's the only place where you would have a local extrema, possibly, and what would be the value of it there? That's the x value. The y value would be log of 1 minus 2 last part, plus 3. That would be at log of 2. Okay? So it would be at the point x equal -1, -1 log 2. That would be your local extreme. Now, which would it be? Positive or negative? I mean, maximum or minimum? Second? Someone said maximum? Any reason why it would be? Okay. Let's see if we can think on that. Log of this value here as x. If x is a very small number, like close to 0, very, very small number, point, very small. So very, very negative number. Let's go to the other side. X is very large. This thing just keeps getting larger. So yes, I would say it has to be a minimum, not a maximum. Because I believe out here you would have numbers that are going like this. You know on the other side they're going like this. Now maybe you don't have any either, but it just seems like to me that would have to be so less than -1.
I'll say it's minimum.
Second?
Yeah, I'll say it's minimum.
Okay.
The original problem, there's no way
It just seems that way. And sure enough, they do show it in the book that if you were to graph that thing, that is a relative minimum. Okay? Good deal. They didn't do the second derivative. You could have done that. Been sort of a pain in the neck, but you could have done it. All right. Homework exercises 5.1. Do any of, sorry. Do either 5 or 7, they're both at Calc Chat. I would do all of 9 through 12, only the odds are available 9 and 11 at Calc Chat and in the back of the book, but you should be able to do all 4 of those. It's just matching. Then do any of the odds 13 to 17, they're all at Calc Chat, 17's at Calc View. Do 19, it's both at Calc Chat and Calc View. Do any of the odds 21 to 29, they're all at Calc Chat, 23's at Calc View. Do any of the odds 33 to 35, they're all at Calc Chat, 31's at Calc View. I may have said 33, 31 to 35, they're all at Calc Chat, 31's at Calc View. Do 37, it's at Calc Chat. Either 39 or 41, they're at Calc Chat. Any of the odds 43 through 65, there's a whole bunch of those. They're all at Calc Chat. 45's at Calc View. Do any of the odds 67 to 73, they're all at Calc Chat. Either any of the odds 75 to 79, they're all at Calc Chat. 77's at Calc View. Either 81 or 83, both at Calc Chat. 81's at Calc View. 85 should be at Calc Chat. Any of the odds 87 to 91 should be at Calc Chat. 93 should be at Calc Chat. You can explore doing 95 or 97, or think about doing 97. Those should be at Calc Chat. There's a couple true false, 99 and 101. You could do those. They should be at Calc Chat. And then there's some applied problems. 103 pertains to home mortgages, which you'll probably hit in the future, so go on and get used to it now. 105 is modeling data. Tractrix is 107. 109 is a conjecture, and you can do any of those you want. They should all be at Calc Chat. I'm not sure I can make out the football field on page 323. That looks like it could have been Tuscaloosa with all the red there, but it could also be Nebraska. Can anyone make out the end zone there? Whatever, it's not important. Okay. Any questions so far? All right. So I think we went to the last slide just a little bit ago. So let's discard that and go to 5.2. All right, that's not looking good so far, but let's see if we can improve it. That looks pretty bad, doesn't it? But let's move to the next slide. All right, 5.2, the natural logarithmic function integration. 5.1, we did differentiation. We should be able to do integration pretty reasonably. We'll use the log rule. Whoa, do we have a log rule yet? For integration to integrate a natural function. Obviously, they don't go and give it to us. We'll integrate trigonometric functions as well. So here's the log rule for integration. All right. Differentiation rules. What was this one? What's the absolute value? What's the derivative of log absolute value of x? 1 over x. Perfect. You don't need absolute value signs anymore. And what's the derivative of log u? Absolute value u. U prime over u. Perfect. Now, let's go backward. Do an antiderivative. That would be the integration rule. Okay? Log rule for integration. Let u be a differentiable function of x. Then the antiderivative, or the integral of 1 over x dx, would be what? ln of absolute value of x plus c. Don't forget your plus c, because that's an indefinite integral. What if this was the case? Antiderivative of 1 over u du. That would be the log of absolute value of u plus c. It just changed the dummy variable on you. It doesn't matter what your variable is, that's it. Okay? So now we can actually do that integration we couldn't do before. Remember, you couldn't do it when the n was -1. Now we can. The log function. Okay? Because du is equal to u prime dx, the second formula can also be written as the antiderivative of u prime over u dx would be absolute value of u plus log of absolute value of u plus c. And it just seems like that's the very same thing we just did, isn't it? Log of absolute value of u plus c. So, oh, I see what they did. They changed 1 over u to be u prime over u. No. Well, no, that's not it. Oh, okay. They got this to be a dx. It was a du before, so when you put it in like this, it's a dx, and that still gives you the same answer. Just a weird way of writing it. Okay, so let's do this. Say again? Okay. Yeah, okay. So what would this be? What's the first thing you could do? Move the 2 out front. That'd be 2 times the log of 1 over integral of 1 over x dx. And what in the world is the integral of 1 over x dx? Say again? The log of absolute value of x. Okay? That is exactly 2 times the log of, so the derivative of 1 over x dx is the log of absolute value of x. Remember to put your plus c. Okay? Now, here's what else you could do. Remember how log of something raised to the power is 2 times that? You can take the 2, move it up here, and guess what? You don't need absolute values anymore, because when you square positive or negative number, that just comes out being a positive number. So log of x squared plus c. So that's actually the simpler way to write that. So you remember your log rules can go both ways. You can bring the exponent out in front, or you can move the coefficient up to make it an exponent. Does that make sense? Say yes, okay. Now, because x squared can't be negative, you don't need the absolute value bars anymore. Unnecessary and final form of the antiderivative. Okay? All right. Trying to find this in the text. Yeah, that's another page over. So let's back up and do example 2, 3, and 4 if we have time. All right, let's do example 2. Whoa, I got to get my pen back. All right. Example 2 says find the antiderivative of the integral of 1 over 4x minus 1 dx. What in the world would that be?
Kick the 1 out, then it's going to be the logarithm of 4x minus 1.
Okay. The logarithm of 4x minus 1, is that what you said? That's a good first start. That would be the log of absolute value for x minus 1. Whenever you do this, you have to put in the absolute value bars. Okay, but then you got something else to do. And this is not a very pretty math term, but I like to use it. You sort of have to unchain rule it, don't you? Yes. What would you be doing there? Okay, I wouldn't do anything with a -4, but what do you do? Any ideas? If you're differentiating, you would, chain rule would have you multiply by 4. So since you're doing an antiderivative, guess what you do with the 4? Divide by 4. So this would be over 4, okay, which would be 1/4, right? Okay, which you could then do as the log of 4x minus 1. And this way you would still have to do the absolute value bars to the 1/4 power. Why? Because you can't take an even root of a negative number either. Now,
plus c too, right?
and yeah, and you got your plus c. I should have written that down earlier. But that's why in this case, I don't see this as being any simpler than that. When it was a square, you could put up there and lose the absolute value. That's worth it. When you put a 1/4 up there, it doesn't really benefit you much, but it is true.
So you can't put it.
And they actually left it in this form right here. They didn't do that last part. And it's not necessary to do it. Okay? You can if you want to. It doesn't make it wrong, but there's that's how it goes. Okay. Now, let's do example 3. I have sort of a weird title for this one, so I'm not going to even mess with that yet. Well, yeah, I guess we will. Finding the area with the log rule. Okay? So find the area of the region bounded by the graph of y is equal to x over x squared plus 1. Okay? So there's the graph, there's the y function. Also going to be bounded by the x-axis, and it'll also be bounded by the line x equal 3. Now this is almost going to require us to do a graph, okay? I sort of hate that. But if you will, just look at the one in the book. Okay, well, some of you don't have books. So let me try to do the graph of this. Okay. That's pretty far apart, but we'll live with it. Okay. Okay. This is what we're talking about. This is x equals 3, so that's that boundary. X-axis is that boundary, and here's the curve. Y is equal to x over x squared plus 1. Now, I just drew it like they did in the book. I didn't do analysis. You can actually plug in values, and I got this way too low here, but you get the general idea. Okay? Now, if that was indeed your graph, okay? And by the way, this only goes up to something about like 0.5, which you don't need to know, but just to give you a perspective of it, okay? How would you go about finding the area under there? How would you find the area under that? This area right here. Wouldn't you do your little rectangles? What's the length of that rectangle? The height, right? The dx. So the total area under this would be the integral from 0 to 3, since we see this starts at 0, if you put in this isn't making a lot of sense. Wait a minute. When x equals 0, yeah, you have 0. That makes sense. Okay. 0 to 3 of x over x squared plus 1 dx. Your dx is the thickness here. Okay? The height of that rectangle is your x over x squared plus 1. The thickness is dx. You're summing those or integrating those from 0 to 3. There's your integral. How do you solve that? Oh my goodness. How do you do that integration? Okay. Don't limit your mind here to just what we've just been talking about. Let's expand back to what we were talking about a little earlier, like 4.5. What would you have done there if that was your problem in 4.5? What was 4.5 all about? Say again? 4.5. It wasn't that long ago, like maybe a couple hours. .5 was? Anybody? What's the title of 4.5? I'm sorry? Integration by substitution. Here's the integration. Is there any way we can substitute and get that to work? What was the rule? U equal the most complicated part of your problem. The innermost part of the most complicated part. What would that be? That would be that denominator, which would be x squared plus 1. Then, what's your next step? du is equal to 2x dx. Perfect. Well, here we have an x dx, not a 2x dx, so let's divide both sides of this by 2. Okay? Now we've got a du over 2. So what we're going to do is change this integral to being, here's the 1/2, there's the over 2 part. You have a du here then, and down here you have just u, right? Because that was what your U was. Okay? U is, U was. Okay. Now what have we not done yet? We have to change our limits. Okay? So down here this tells us when x, the dx here, when x equals 0, what's u? 1. So u is going from 1, and then when x is equal to 3, u is, second, 10. Excellent. All right. Now what do we have here? 1/2. And what's the antiderivative of du over u? Please tell me you know that one. Okay, what do we do in 5.1? Or actually, just a little bit higher in 5.2. Right there. Or here, actually this one's better. What does that tell you? Log. It's the log of u. That's what we're just doing. It'll be the log of. Now, do we need to put absolute value u? Why not? U is going from 1 to 10. It's never negative. So you don't have to put the absolute value. Log of u evaluated between 1 and 10. Okay? So what would this be? 1/2. Log of 10 minus log of 1. Well, what's the log of 1? 0. So there we have it. 1/2 log 10. There's the area under that curve. 1/2 log 10. Now, if you have a calculator and want to put those numbers in, they claim that's approximately equal to 1.151. Okay. Not exact, but close, because logs are usually irrational numbers. Not always, but quite often. Does that make sense? So that was example 3. All right. The question is, do we have time for example 4? What's that?
You got to pay time to see.
Oh, that's true. Okay. So, we'll pick up with 5.2 next time. Okay? We're going to do, hopefully finish 5.2. Oh, let's see. Or a few homework exercises. You wanted me to give you those too, I know. So let me give you those. You can do any of the odds 5 through 27. I think you can. At least get started on those. And those are all at Calc Chat, 9's at Calc View. We'll worry about the rest of those next time. We may not do quite as much with 5.3, okay, because I'd love to get into exponential functions, differentiation, and integration. Those are so much fun. They're great to do. So we'll probably maybe do a quick slideshow of 5.3, then do 5.4. We may or may not do 5.5. We'll see how much time we have. Okay. Now, y'all have been very anxious to get your tests. So let me find those for you. And please, folks, get your last test, or 2 tests, depending on who I'm talking with, in. I don't think the one person who hasn't turned in test 2 is not here still. Somewhere here, I think. Yeah, here they are, I think. All right. All right, here's your test 4, which will be your final exam. Final test. It's mostly chapter 4, maybe just a little bit. All right, we do. So you're missing 3 people missing today. 1, 2, 3. Good deal, thank you. All right, have a good weekend. We will see you Monday. Looking forward to it. Morning, how are you, sir?
Still here.
Good. Always a good sign.